yeah, so I'm going to go ahead and introduce Siva Reddy, our speaker for today. So just a little bit of background from him. He's a postdoc in the computer science department at Stanford University, currently working with Professor Christopher Manning. His research focuses on enabling natural language communication between humans and machines. And prior to this postdoc, he was a Google PhD fellow at the University of Edinburgh under the supervision of Professor Marilla Lapata and Professor Mark Steedman. And for some more info on the talk that he'll be giving, he will present his work on CoQA, which is a novel data set just released this past August for building conversational question answering systems. CoQA contains 127,000 questions with answers obtained from 8,000 conversations about text passages from 7 diverse domains. The questions are conversational and the answers are free-form text with their corresponding evidence highlighted in the passage. And Siva will analyze CoQA in depth in his presentation and show that conversational questions have challenging phenomena not present in existing reading comprehension data sets, for example, co-reference and pragmatic reasonings. So please welcome Siva Reddy.
Yeah, thank you, Zach, and thank you, Sanjana, for inviting me here. And I'm very excited to see all of you. This is my first time, I think, coming to an industry and giving a talk. Like I did other companies like Google, but in a meetup, this is my first time. And I see there's a lot of interest in NLP and machine learning everywhere now. How many of you do NLP here? NLP or some machine learning? Oh, wow. Yeah, that's quite a lot. Okay, so I guess what's happening in our field right now. Question answering is one of the hot topics right now, and also it's very useful. And today we will talk about conversational question answering, and we call this CoQA. And this leaf stands for this tea. It has multiple meanings. One of them is like coca tea leaves. I don't know if you guys know it. Yeah. This is a joint work with my collaborators, Dataset, and my supervisor, Chris Manning. Okay, so coming to question answering, so let's take this passage here. You have a computer that's reading stories and then trying to answer questions on these stories. So here we have Jessica went to sit in her rocking chair. Today was her birthday and she was turning 80. Her granddaughter Annie was coming over in the afternoon and Jessica was very excited to see her. Her daughter Melanie and Melanie's husband Josh were coming as well. And Jessica had, and you have some more text here. And now you want a system to answer questions like whose birthday it is. And if you have this question, it's very clear that it's Jessica's birthday. So it's not that straightforward. Today was her birthday. So you need to know that her refers to Jessica here. You can try and write a lot of rules for this, but those systems are very brittle. And then who is Jessica's daughter? And again here you have this sentence called her daughter Melanie. And you should know that this her again refers to Jessica and not to other people like Annie, who is also referred with her at some places. Okay, so you have this set of isolated questions. You try answering those questions. At any point of time, if you have any questions, feel free to stop. That's okay. Okay, so why should we do this? You already know, one of the famous question answering systems is Google question answering system. Whenever you type a question, you directly get an answer, and most of the times you get an answer from a document. So here, what is the original color of the sky? The answer is blue, coming from a document which is from the exhibits.org. Okay, and it need not always be correct. Sometimes you can even get wrong answers. And many problems in NLP these days can be formulated as a question answering problem. If you have a sentiment analysis problem, you can say, okay, what is the sentiment of this document? That's another question answering problem. You could also something like, what is the summary of this document? And then that's also a question answering problem. So whatever progress we make in this particular problem, that means you make progress in many other problems. And like after deep learning revolution and also after the release of Stanford question answering dataset, how many of you know this dataset, Squad? Oh, cool. Yeah, a lot of you. There are also many startups around this dataset now. So here, this is the task we have seen earlier. And like human performance on this is like 82 exact match or 91 approximate match. And if you see the current models, like BERT, this came in 2 weeks ago, it's exceeding human performance by like 2 points already, which means like machines are better than humans in answering these questions. It's controversial to say that machines are better than humans, but like at least in this evaluation setting, like it seems machines are performing very well. And also, once this data set came out, like there are so many variants of this data set now, like you can find 6 to 7 data sets already focusing on different aspects. Okay, and like you can ask me like, is there something beyond question answering? Right now, one of the major limitations of these question answering systems is you cannot have a conversation. It's a very limited context. They make use of very limited context. You can ask isolated questions, but you cannot ask different questions. So there's like, is there something beyond what current setup? And this is coming from a 1981 paper by Phil Cohen. He's a founder of, I think, founder or director of Semantic Machines, or not Semantic Machines. What is it? Oops. He also did that. I think my wine is working. I should remember that name, but I couldn't. Okay. So they say here, like, we will demonstrate using protocols of actual interactions with a question answering system that users of these systems expect more than just answers to isolated questions. They expect to engage in a conversation. And like the more interesting thing for me here is the next sentence. Moreover, they maintain these expectations even in the face of strong evidence that the system is not a competent conversationalist. So if you are a startup here, like trying to build question answering system, and if you deploy this in the wild, people are going to have a conversation even though it's not built for a conversation. So it's you have to be very careful, and you have to try and answer conversational questions too. And this is where we are coming here. Like we are launching a new task called conversational question answering, and we are also creating a large data set. I'll go through this. So this is the same paragraph we have here. And now I'm trying to test like who can answer these questions. Like, so if I give you a question like who, can you answer this question on this paragraph? Can any of you answer this question? Jessica, okay. But like most of you are not very sure, right? Okay, I would say like the previous question was, so there was some conversation happening, and the question was how many, and after that question, this question appeared like who. And now can you guess your responses to these questions? 80, okay. So if how many was 80, then who is Jessica is kind of makes sense. But like I'm also giving a previous question here. Did Jessica plan to have any visitors? And the answer is yes. And how many? 3. And who is Annie, Melanie, and Josh? Yeah. So you're wrong. As you see here, like a conversation plays a major role in answering questions. If you try and answer these questions independently, you just saw what happens. So you need to understand the context and keep the machines has to remember what has already been talked about. Okay. So like our setting is kind of a limited setting. It's I would say it's not ready for deployment yet. It's the limitation is that here we have this conversation which happens in multiple turns, but we limit ourselves for each turn contains just a question and an answer. you cannot talk about anything else. So like, but that's not like how we talk, right? In a real conversation, you might ask a question and then I will answer that, and then I might ask you some question or some clarification question or something else, or I might say some joke. But like we want to make progress, so like this is a good place to start. And like two people are talking about a story here, and one person asks a question and the other person answers the question. Okay, that's the setting. And then all these questions and answers are in free form text. If you see Squad, for example, so answers in Squad are limited to spans in the passage. So you, whenever there is a question which does not have an exact span, you would not see that kind of question in the data set. Whereas we want to have more natural questions and answers here. And I will go into more detail later. And the other thing is, it's really easy to track progress on conversational question answering. So if you take, like, if you're working on dialogue systems, you know that evaluating these systems is really hard. If you're building like something like Microsoft TA, so this is a chatbot for Twitter, and you know that like they deployed this in the wild, and what happened? That was a disaster. The reason was like it's really hard to evaluate how well a chatbot performs. Whereas in our case, you have this conversation grounded in the given story, so it's much easier to say whether a response is correct or wrong. Okay, and this is also a challenge for you guys. Like I'm saying, like if any of you in this room claim that you have an intelligent dialogue system or conversational system, first thing you should do is like try and pass our test. So it's a very easy task for humans. So we expect that any conversational system, intelligent conversational system, should pass this test. Okay, so what is CoQA? Like CoQA is this data set for conversational question answering, and we handmade with love. It's not just us. Like there's so many workers who created this data set, and it has like 127,000 questions and answers. You could really build a good system exploiting all this data set. And if you take each conversation, like you have 8,000 conversations, and each conversation is on average 15 turns. So sometimes you can go up to like 30 questions and answers. So which means like some question, like 20th question might depend on something like 10th question or first question. So you see like how context dependent it is. Like it's a really hard data set, I would say. But as I said, like it's a much easy task for humans. Like if I and Jack answer the same question, like we would agree on our answer like 88.8. So our answers would, if you take word overlap match, we would have like 88.8 F1 overlap here, which is quite high. And like we also created data sets for several domains. So we'll see all these in detail. So like we created this data set with three main goals in our mind. So one of the first goal is we want to have a conversation. That's the first goal. So if you take this passage about Virginia's governor race, so there's two people competing in governor, Republican, Democrat, and so the question was, what are the candidates running for? And the answer is governor here. And you see this context dependence now. Like the question is like where, and where is referring to this event running here. And this is in Virginia, so you have Virginia. But like if you try to answer where independently, you might also say Richmond, which is wrong. There are other places in the passage. And who is the Democratic candidate? So it's Terry McAuliffe here. And if you see here, like who is his opponent? Now the focus has changed from that event running to this entity Terry. And it's also interesting, like the second question was dependent on the previous question, whereas the fourth question was dependent on the third answer. So it's like in conversations, we try to have this context dependence on questions, answers, on some other terms, not just the previous term sometimes. And like, and here, who is his opponent? annotator said that Ken Cuccinelli, but some of you might say that the candidate is, you could also answer this as a Republican. Who is his opponent? It's a Republican. When you say Republican, the next question would be what is his name? But in this case, because you answered as Ken Cuccinelli, the next probable question is what party does he belong to? So depending on the answer, your question might also change. It's conversation-driven question answering. And which of them is winning? So here, them means right now it's referring to two different things. So it's not that straightforward what refers to what. So it's a much harder problem. Okay, so that goal, you have a lot of questions like that in the dataset. The other thing is we want to have free-form conversation. So when you deploy it, it feels natural. Something like so like to collect this data set, we tried various things, and the thing that worked for us is something like this. So if you have a question, how old would she be? In our passage, we have this, she was turning 80. So that's the sentence given in the passage. But like the answer we want here is 80. So we ask our annotators not just to write the answer, but also try and find an evidence in the, so they first highlight some sentence in the passage and then take that sentence or evidence and edit that thing and write the answer. If you don't do this, what might happen is that somebody might write 80, they might spell 80, E-A-G-H-T-Y. And then when you evaluate your system, when you train your system, like this a disagreement between answers. So systems do not know that 80 is different from E-A-G-H-T. So they think they are different even though they are same. So it's much harder to train models when you have different answers. We want to have same answers. And in this case, like who, the annotators first highlight the whole evidence. So here you have this evidence spanning across sentences, but the actual answer was Annie, Melanie, and Josh. So like it's also they're following the order in a way. So it's when you make annotators do both the evidence selection and then writing the answer, you have a lot more consistency in your answers.
Wait, so can you explain that? So basically, because it shows up as the numerals 80 in the text.
Yeah.
It's like it's the answer. You're expecting the annotator to write the answer that's most consistent with how it's set.
Exactly. Yeah.
Okay.
Yeah.
What if the answer doesn't exist?
Oh yeah, it's. Oh yeah, there are many cases where the answer may not exist in the exact form, like yes or no questions, for example. You may not see yes or no in the passage, but like you still know the evidence sentence, right? And then you highlight that and you write the answer as yes. So this is also useful for training models. So you know, you can force the model to look at some evidence before writing an answer. So if you're deploying it publicly, you have not just the answer, but also some evidence which people can see and figure out whether this answer, whether they can trust the answer or not. Okay. So like our, because of this procedure, like we found that 66.8 answers can exactly be found in the story, which these are called extractive answers in the literature, and like 33% are not exactly found. There's some form of variation to the text span in the story. So it's a good news for training models in a way. And also like human agreement here, as I said, like it's quite high. So if you, I'll skip that one. Yeah, the other thing is when, oh, go ahead.
So as far as abstracted like who did she intend to invite to the party, or how many people?
Yeah. How many people is an abstractive answer, because that's not present in the story in its original form. Yeah, like, and we also want systems that are trained on multiple domains so that they work well on unseen domains. So here we made sure that we collected data sets from like 7 different domains: children's stories, literature, exams, CNN news articles, Wikipedia articles. So we provide training data sets for these 5 domains, and the remaining 2 domains here, like these are hidden. We want to see how well your systems generalize on these hidden domains. So the hidden domains are Reddit and science articles. Okay. And comparing like CoQA with Squad, in CoQA we have conversational questions, whereas in Squad you have these isolated questions. And our answers are abstractive, and we also give you evidence for each answer, whereas Squad you just have extractive answers. So you do not have any abstractive answers in Squad. And we cover 7 domains, and Squad has single domains. And we'll also give you some more qualitative analysis, like what happened, what are the differences. So our passages are longer than Squad. One interesting phenomena we found is if you take question lengths, when you're having a conversation, because you're trying to build on what happened previously, your questions are generally shorter than when you're trying to cram everything into one single sentence as a single question. So questions in conversations are shorter than questions in isolation. And similar argument also applies for answers. You can't read this figure, but like I want to tell you what happens in Squad and what happens in CoQA. So in Squad, because of this isolated phenomena, you would not see any thing like he, she, it, or any of these phenomena that's referring to previous questions. In CoQA, you see them quite a lot. So the most predominant trigram in the dataset is what did he in CoQA, whereas like in Squad is what is the. You would never see anything that has co-reference. And also the number of questions, because we want to have this natural form, dataset with natural form of questions and answers. We have a lot of questions like which starts with various words which are never seen in Squad. And also our questions would just sometimes have single word like what, where, and that kind of questions which you would never see in isolated question asking. Okay, coming to linguistic phenomena, the most predominant phenomena we have in our data set is this dependence on previous questions. So you have a lot of co-reference phenomena. This is an example showing you how important is co-reference phenomena. So there are these 2 people here, and one person is carrying a baby and a napkin, and this person asks, where did you go? I was looking for you. And the person in green color says, I had to go change baby's diaper. Do you mind throwing it away for me? And then this person in gray, no, he replies, I don't mind, and then throws the baby rather than napkin. So like it refers to napkin than the baby, but this person doesn't understand co-references. So disasters could happen if you don't understand co-references. Okay. The other kind of phenomena we see is a lot of paraphrasing. So you might have some question that that may appear in different format than that's present in the story. So that's paraphrasing. But we also have this interesting section called pragmatics. So if you ask me what time is it, okay, and the passage has something like the milkman just arrived, so that's the evidence, which means like what time is it? You would answer it something like morning or like 10 o'clock, 8 o'clock, whenever your milkman comes. So like this is a much harder class. Like you humans, like we infer a lot from the world. And also like we have other classes like how many, ranking, who is the first or second, give me the 10th person or something like that kind of thing. And causality, like where we ask like why did this happen, why did that happen. And also there are some questions which you cannot answer no matter what. Like if you say how old was Annie in the first story we saw. Annie was the granddaughter. It's not given in the story, so you cannot answer that question. So you also have that kind of questions in your data set. Yeah.
On the pragmatic, does that mean the answer is sort of not answering the actual question, but trying to get out what the questioner was wanting to know?
Yeah, exactly. Yeah, okay. Yeah. The question is answerable, but it requires some external world knowledge. Yeah, it's
So the person asks, "What time is it?" and the response is, "The milkman has just arrived."
Oh no, that's not the response.
Oh,
yeah,
right.
that's the evidence in the passage,
Okay.
but the response would be probably morning.
Oh, okay.
Yeah, that would be the response. Yeah, but that's probably morning was never present in the story in itself.
Right. We know because of the milkman.
Yeah, that's right. Yeah.
Okay.
Yeah.
How do you deal with questions about how local answers?
Oh yeah. So we collect answers for each, like four. We have four answers for each question. So hoping that like at least some answers match when you predict something. Yeah. And we think like this data set is quite hard compared to existing data sets, because like in existing data sets, people showed that you could use simple string matching, building heuristic methods to find answers. And also they are easily distracted. So something like if you have, I did not eat. So if you have something like that, if the question was, did he eat? Because there's eat and eat there, they just say yes in this case, or like they get distracted easily. And because of the phenomena we have here, like co-reference, pragmatics, and out of domain evaluation, it's hard to cheat on this data set, I guess. The good thing is we also have this rationals, which is the evidence. So when you build models, you also have explanations for your answers. So that's much more useful for people. Okay. Yeah, that's the dataset part. Like we'll go more into models. If you have any questions about the dataset, you can ask me now. Yeah. Hi.
How would you enforce variation?
Oh, variation in.
When you're asking. Do you use any kind of?
Oh yeah, good question. Yeah, so like how do we get diverse set of questions, right? Yeah, that's the question. We had a qualification test which has like several kinds of questions, and people had to pass that qualification test. But like we wanted to have like natural conversations. So I mean, even though they pass this qualification test, they have to work for 2 to 3 months. So they might have forgotten what we gave in the qualification test. The main incentive was we want to drive the conversation as much as possible. So hope is that because there are 2 people here involved and we pay them per turn, so the conversation length goes. If the conversation length is long, they get paid more. That's one incentive. And the other one is we also ask people. So if you and I get partnered in this hit, so when I am asking you some good questions, we ask other people to find out, oh, these people are good or these questions are good. So we have that kind of feedback to try and rewarding good people.
Can you give some idea how hard it was or how much work was involved in building it?
Oh yeah, there's so much work. I also have some after this model injection, we would talk about how hard it is. Yeah.
So when you talk about the F1s, was that like, what is the F1 for me? I think F10.
Yeah, right. So this F1 score is nothing but like a word overlap, like how many words overlap between your response and my response. So it's like a precision and recall, and you take that. Yeah. Yeah, it's like you can take it off something like if you and I answer a question, 88 percent of words are the same in the answer. Yes, yes.
Considering how the class of questions that balance service like as compared to like the most dominant.
Oh yeah. I mean, like that's a so the most dominating class might influence the metric. Yeah, like one way to eradicate that would be to have class-wise results, like question type-wise results. So the predominant questions we have are what kind of questions, and also yes or no kind of questions. So they would have, I guess, like stronger agreement, even higher agreement. And the questions which we would have lower agreement would be something like why. Yeah, that's a good point. Like we did not have that results. Yeah.
So and the
Yeah, these are macro average. Yeah.
can I prove it essentially that
Oh no, it's hard to fool because like even if you do very well at one class of questions, there's so many other classes, right? If you see that figure which we had earlier, so this you have so many class of questions here. So it's if you just do well on one class, it's not enough. Yeah. I mean, you could always take those responses and do more analysis on what happens. Okay. Okay, let's see like how we can build models, and we will use deep learning for this. So if you are familiar with dialogue literature, the way people these days build chit-chat models, for example, is you have this class of models called sequence-to-sequence models. I guess everybody must be familiar with this by now, where you read in the whole thing and then you try to generate the answer. Okay, whatever you have, word by word, that's sequence-to-sequence generation. So the sequence is what you talked already, that's your input, and the output is what you're going to talk or what is your answer. That's the sequence-to-sequence model. So we call them conversational models. And the other models here, reading comprehension models. So these models try to find evidence in the story rather than trying to generate answer. They try to stick to the words in the story. They try to identify spans in the story. So they are kind of limited because you can't answer all kinds of questions like yes or no, which we already talked about. And then we have this hybrid model, which does both. It tries to find some evidence in the story and then try to generate the response. I'll go into more detail. You have an idea. So this is a sequence-to-sequence model. So in this model, the way you would start is like you would have a fixed vocabulary you start with, and like your response is going to be only in every word in your response is going to be in that fixed vocabulary. So at every point, your goal is to. So this is your vocabulary distribution you start with. So if you say I start with like 10,000 words, okay, your goal is to generate a word at each turn, at every timestamp. Okay, so let's take like how we do. So a sequence-to-sequence has an encoder and a decoder. So the encoder takes the story here. So this is the Virginia's governor race, blah 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 blah. So you have the story, and you have so the other thing is you have the questions, all the questions until this nth turn. So you have first turn, what are the people running for? That's your first question, and you would have an answer, and you would have second question. So you're like treating the story and the dialogue as one chained sequence of input, and you mark. You have these markups called questions and answers. Q stands for question, so that indicates that okay, until now we read passage, and now we are going to read the question, and this is answer, and this is another question answer, and then you have finally you're trying to answer this question where. See that like it's a pretty naive model that you have to read in the whole thing at chain sequence, and then encode the whole chain sequence into some representation and trying to decode an answer from that representation. And the way you decode is like you start with, so you have this start point which you're starting decoding, and at each timestamp, what you would do is try to find out what words are more important for your response at this point, and then get an attention on the encoder stage. So this encoder represents each of those words into some form of embedding, and now you're trying to find out, based on the decoder state, what words are important, and use those words to build a context vector. So that's a context vector. And you take this context vector and the decoding state and generate the current word, the current word in the response. So here, your hope is that Virginia is already in your vocabulary, and then that would have higher probability than any of the words. And you would do this until you predict end of answer response, so that you keep generating the answer for a given term. Yeah.
Is any information about the distribution of the intention in the context vector?
Oh yeah, so that would be from the question. So these are you also have the questions here, right? So it's not just the passage, but also the questions. So like where when you see where, probably the model thinks I should highlight places here.
The context vector isn't the sum across.
Yeah. It is a sum of all these encoder states. Yeah.
How did you deal with the varying lengths of the inputs?
So here it doesn't matter, like, because you're taking an average. So even if you have 100 words or 200 words, in the end you just end up with one context vector. And for each word, you would just have an attention distribution saying how important is that at this current timestamp.
Just from a practical standpoint, did you have a fixed length and you added either sequences that are shorter or longer?
Oh yeah, you have to do that. Yeah. So when you do this in GPUs, so you would have, because you have varying length passages, varying length questions, so you have to pad a lot of things. Yeah.
So then how do you deal with different passages and
Oh, so what you would do is, like, you would have a mask vector, this thing called masking, where you would also you would have a batch, and you would also have a mask matrix which says which words are valid and which words are like dummy, and you would just have zeros there. And
yeah, I guess my question is just like, if you have a long passage or a shorter passage, then you can, the number of questions you can fit in can be variable.
Yeah.
Per kind of example basis. So how do you rectify that difference where you have one example having one question because of the length constraint versus another example having 3 or 4, as you mentioned? So
yeah. So like,
seems like it'd be adversarial to like training.
yeah, so what we do is, like, we have a batch for each story, so that like you have the whole passage that's constant for all the questions, and then the dialogue keeps varying, so that means the first question would have a lot of padding, the second question would have little padding, and that as it goes. But like, you have to sacrifice something. Yeah.
So those red squares are LSTM.
Yeah, this is a bidirectional LSTM, trying to build a context-sensitive representation of each word. Oh yeah, we also use embeddings for globe embeddings and things. Yeah.
You sometimes take the output of your final distribution and feed it again to the decoder. So that depends if you are having a normal conversation, depends on what answer your system gives.
Right.
So let's say now you are doing a prediction. Your model is trying to give an answer. The moment it gives an answer, the next question sometimes can depend on the answer.
Oh yes. So we give gold answers in those cases. So it's not the predicted answer at each step. We give the gold answer. Yeah. we will see another interesting model. A limitation of this model is you're assuming that you have this fixed size vocabulary and your response is going to be always the words in your response are going to be in this fixed size vocabulary, but that's not the case. Even if you start with 10,000 words, there might be many words that are never present in your vocabulary. So you have this sequence to sequence with copying models. So the intuition here is that for most questions, you would see a lot of words that are already in the passage. Even though they may not be in the vocabulary distribution you started with, the answers might already be in the passage. So what you would have is two distributions now. You're trying to learn two distributions, not just one distribution. Where one distribution here is the generation distribution. So that's a fixed size vocabulary distribution. Like you have 10,000 words and you're going to have probability for each word. That's the generation distribution. And you're also trying to learn this attention distribution, which corresponds to copying, how likely you're going to copy that word. So this is limited to just all the words in your passage. So it doesn't matter if it is an unknown word, which is not in your vocabulary or not. It's going to be like one, it's always going to be the words in the passage. Okay. So now you have these two distributions. One is a generation distribution and the other is a copying distribution. You take both of them to generate the final answer. So in this case, like Virginia, even though it may not be in your vocabulary, it might the model might figure out Virginia is already in the passage and I have to copy it in my response. Okay, so that you have a final distribution that is a weighted distribution, weighted sum of copying distribution and a generation distribution. So this sequence to sequence with copying. Yeah. A good thing about these models is that these can generate responses that may not be present in the story. Like here, because you have fixed size vocabulary of 10,000. So even if a word like yes or no or this counting, some of these, even though they may not be present here, they will be present in the generation distribution. So you would be predicting words that are not in the story, and also words in the story. So it's best for both. And the other model is this machine comprehension model, which is what we're going to do is until now we generated answers. Now we are going to find evidence in the passage rather than generating answers. We're always trying to find where the answer is in the passage. So you would have a start point in the passage and an end point in the passage saying that, oh, this span corresponds to my answer. So the way we try to identify is like you would have a different encoder for question. So you first build some embedding representation of a question. So you could use anything, like what we used is a bidirectional STM. So you have this dialogue history and the current question. We pass a bidirectional STM, get embeddings for context-sensitive embeddings for each word, and then merge all of this using some self-attention mechanism to get one representation for a question. So you have an encoder for a question, and similarly you would have another encoder for your story. So in the previous case, in the sequence to sequence case, we had only one single encoder that takes the whole passage and the history and then trying to generate. Whereas here you have two different encoders, one for question and one for passage. So this is the passage. Again, you use a bidirectional STM to get context-sensitive representation. And then what you would do is, now you have a representation for each word in the passage, and you know what the embedding for question is. And your goal is to find out what is the start span of my answer, right? So you would try and build a classifier by comparing, let me show here. So you try to learn a classifier which says how likely first word is going to be a start span, how likely second word is going to be a start span, third word is going to be a start span. So you assign probabilities of how likely something is going to be a start span. So that's a weighted, that's a classifier which takes question representation and each word context sensitive representation and assigns some probability. And similarly, you would have another classifier which says how likely that word is going to be an end span. And now you try to find a start and end span that has maximum probability of taking both start and end spans here. Okay. Yeah, there's so much going on here, but like you should remember, like this model, because it's limited to start and end spans in the passage. If some word is not present in the passage, like yes or no or like numbers, it would not be able to predict an answer for those questions. So it would. So this is the limitation of a reading comprehension model. Okay, the best. Yeah.
What if the answer needs to be like that?
Yeah, it can't. That's a good question. So if it requires two different highlights from, it would just pick the one which has the highest probability, one of those spans. So in this current setting, we always take the span that has highest probability.
The end can be short before the start, right?
The end can. Oh, that's a good point. We do not consider those cases. If end, you could just throw away that. Whenever, if your end point, right. So what we do is, like, from each start span, we consider only 15 words to the right, and just take those words, whichever has highest probability.
So you're basically limiting truncating your attention.
Yeah, like I mean, like if this word was a start, so we're trying every word, right? It's not like we are not going to. So our response, the longest response is 15 words. That's the only limitation. Yeah. But like we are going to try every start point and then 15 words from there. Start point, 15 words, and then we combine both of them, both of these probabilities.
Like, so you see every word is the start point, and then you calculate that.
Yeah, yeah, with respect to that start. All right, I will move on here. Like the next best thing to do would be to have benefits from sequence to sequence models and also these reading comprehension models, right? So the thing what we do is like what you have already seen. So if you have a question like, did she plan to have any visitors? So we would have this reading comprehension model that highlights some evidence in the story. And the sequence to sequence model takes that evidence and generates a response from the evidence. So this is like what humans also did. So this handles all the problems. It can generate responses that are in the passage, and it would also exploit the evidence. Yes.
Like end-to-end.
Oh, two separate models. Yeah, very good point. This one. So yeah, coming to the evaluation, somebody asked F1, how do we compute F1? So here, if you take like a question like, what did James do? One response was took the puppy home, and the other response was took him home. If you see like the number of words that are overlapping, there are 3 words, I think 2 words overlapping overall in these 2 responses. So if you compute precision with respect to, like, if you think A1 was the goal response, and A2 was the prediction, the precision would be 2 by 3, and for recall would be 2 by 4, and then you take a harmonic mean of these 2 things. So it's going to penalize mismatches between words. So it gets even worse in questions like why. One response was because he felt lonely, and the other response was because the puppy did not have a family. Yeah, but like evaluation is a really hard problem. Even after that, I would say like we have this 88.8 F1, which is quite high overlap. Okay, coming to the results using this metric. So the sequence to sequence, which is generating responses without copying, that gets like 26, and you get huge bump when you have this copying operation. Okay, but like surprisingly, the best model, this finding evidence, the model called Dr. QA, that's the model which is trying to find evidence in the story. That's the start and end points of your answer. So that gets better than sequence to sequence model. And when you combine both of these, you get quite an improvement. So it seems like using both the extractive and then abstractive is a better approach for dialogue.
How do you combine the two models? What happens with
So there's,
prediction of the two models? How do you combine the prediction?
so you just take one prediction, which is the span, and then you take that span and then generate the response. So it's always like you're taking what one model predicted and then generating. If the first model did some mistake, you may not recover.
So the Dr. QA model present gives the context to the second model.
Yes, exactly. Yeah.
If you look at it looks like almost really. You select the best model from the first model, best prediction from the first model, and then use it for the second.
Yeah.
So did you consider to, let's say, to select the top 3?
Oh no, we did not do that. Yeah. We want everybody in this room to try all the models. Yeah, like just 3. Yeah, even that is good. And then we have this human agreement. So there's still a lot of gap between machine performance and human performance. Right. And also, like, there's some very interesting things we did, like something like how important is history. So if you say like, I'm not going to use all the history. This was the experiment I did with you guys. You remember the question I asked you, a question without showing previous history. So we did the same thing with models. And without showing history, the models get 61.5, which is quite high, I would say. And then showing one turn, they give you a bump like 5 points. But like showing more turns, it doesn't improve. Like the models were not able to leverage. And we thought, like, is it a problem with the data set? So we did the same experiment with humans. And when you do with humans, when we do not show any history, humans don't want to predict an answer. So only one of you predicted an answer, or 2 maybe. So it seems the accuracy is quite low. But like given just one previous turn, you get a very high number. And you show more and more, you get better and better. But it's also interesting that like with 2 turns, you almost get to what you want in the end. Which means like our conversations are kind of limited to 2 timestamps. Maybe that's, yeah.
Shouldn't we be having not more terms? How you ask more questions? For example, I did more in the if you highlight that for something that then it doesn't know which one.
Yeah.
What can be through? Somehow we know as
Right. So we did not allow models to ask questions. So clarification questions is one of those aspects. I think like I'm running out of time, so I'll skip to some of the important other things. Okay. So like, we have better models. We have a leaderboard to track progress. We already have 75 here. We did not show it here. That's a submission. Like, okay, the more interesting part is like how hard was it to collect this data set? It was a really hard thing. We spent like 3,000 human hours on collecting this data set. For industry standards, it may not be so much, but like for academic standards, this is quite high. And also, we paid workers very fairly, and workers really cared about the quality of the data set. It's very interesting that some of these workers also tracked the progress of what's happening to the work they did. So one of the workers replied to one of our paper saying, "This is we read this paper. It's good." It's interesting, like these people care about what they did. Also, we tried many various pilots while collecting this data set. So one of the setup was the questioner was asking why, and the answerer was saying why what. And the questioner was saying decide, and the answer was saying that's not a good question. I mean, this is not the data set you want, right? So we also have provided a little chart interface to find out for them to talk about other things and not pollute the data. That's also very important to make sure data doesn't get corrupted by this. It's also very interesting, like once we provided this chart window, they were talking about how much they're earning that day, what did they take their dog to the walk, or they talk about a lot of funny things. For us, what worked was the answer highlighting the evidence as well as editing the evidence to write the final answer. That worked very well. And for questionnaire, we did not want them to ask trivial questions. We want them to ask diverse set of questions. So we have, as they turn, type feedback. So whenever they are typing some words that are already present in the story, we ask them to rephrase those questions so that it becomes more interesting. The models cannot cheat that way. Also, we have this in-chat window interface. And then like these people, they're like, in my experience, I find them really nice. So whenever there's some mistake, some of you are collecting the data set, if you think it's their mistake, probably it's yours, not theirs. So pay them. And that way, like you would also be popular on the forums, so everybody would want to do your task. Okay. In combination, I think, like in conclusion, we think that this data set has many challenges from dialogue and also reading comprehension. So it might be interesting for some of you guys here. And there's a big gap between humans and machines. And I think like this gap would reduce over the coming years. Right now, it's 15. When we released the data set, it was like 23, and now it's 15. So you could see like we're making huge progress already. This in 2 months. And this also has a lot of phenomena, and some phenomena might be more interesting to you than others. So you could also take a look. And as I said, like AI systems should pass this test, I guess. That's really important. It's such an easy task for humans. Yeah, and if you have a chatbot, what you could do is try and learn a pre-trained model on this task, and then take that model and fine-tune it for your task. So that way, the model already knows how to deal with co-references, how to deal with dialogue history and variations. So that way, you would even though if you have small data, because you're piggybacking on such a big data set, it's much easier to build a better model. Yeah, thank you.